In this video, we're going to be looking at the relationship between x and y values in a data table in order to state if the function is linear or nonlinear. So let's look at the first problem. Number 35 says, determine whether each relation or equation is linear. Justify your answers. So first thing, when I have a data table, what I want to look at is how my inputs, my input or my x values, and remember we call these our domain, how our domain or input is changing, and then how my output or my range are changing in relation to my inputs. So if I look down the x column, I notice it goes from -1 to 0 to 1 to 2. So my x values, or my inputs, my domain, are increasing by 1. When I look down my y values, I see it goes from -2 to 0 to 2 to 4. And what I tend to do, let me grab a new color, what I tend to do is just mark on my data table what's happening. This is +1, +1, +1. Okay? And I'm going from top to bottom, but you'll see in later lessons where we'll look from next to previous and work our way backwards, but it goes both directions. And when I go down the y values, I'm going from -2 to 0, that is +2. Again, I'm going from 0 to 2, that's +2, and from 2 to 4, that's +2. So I have a common difference or a common pattern. Everything in my y values increase by 2 when my x values increase by 1. So let me just take a moment and write that out. As my x values increase by 1, and remember my x values are my input or my domain, listed right up here. As my x values increase by 1, my y values, or my output or range, increase by 2. Okay? So that happens all 4 times. It's a constant pattern. So there is a common difference. So this is a linear function. So we could even say, therefore, it's a linear function. Okay? Let's take a look at the next problem. So on number 36, again, if you notice, in my inputs or my domain, it's the same exact values I had on the previous problem. So this increases by 1, this increases by 1, this increases by 1. It won't always be that way, so you always want to look it over carefully, but here it's repetitive. And here's what's happening in my y's. So as I increase by 1 in my x's, my y increases by 1, +1, increases by 1, +1, but 1 to 4, that's not an increase of 1, that's an increase of 3, so +3. This is not the same value as my x's increased by the same amounts. So if my x's continually increase by 1 and then my y's change what they're increasing by, I don't have a linear function. So let's go ahead and write that, and I'll just stick in green. As my x values increase by 1, my y values increase by 1, 1, and 4. Oh, excuse me, 3. And 3. Okay? Not a common difference. So this is non-linear. Okay? Last problem here. Again, take a look at our x's. It's the same values. So increase by 1, increase by 1, increase by 1. And look what's happening in the y's this time. How do I get from -1 to -1? Well, there is an increase of what amount? 0 plus 0. -1 to -1, again, plus 0 and plus 0. So I add the same amount to my y values each time, so this does meet the criteria for being a linear function, and I can say as my x values increase by 1, so I've used the same intro in each thought, my y values don't change, or increase by 0 each time. Okay? So this is a common difference. So this is linear. And just as a side note, it's a linear function. When you have all of the same outputs for all of your inputs, and we're just looking at it, let me just slide up a little bit so you can see this. If I just draw a real quick coordinate plane, here's my x-axis and my y-axis. This means that for all these different x values, -1, 0, 1, 2, that each time I would be getting out a -1. So that means I'm going to have a horizontal line, slope of 0, a horizontal line that's produced in this linear function. In this video, we're not given a data table, we're given a picture, but we're going to go ahead and make a data table so it goes with this same lesson of looking at data tables and seeing how the relationship between x and y, whether you've got a linear function or not. So our directions say build these houses using the orange squares and green triangles from pattern block pieces. Well, they're built for us in the picture, so we'll go with that. And we have 4 different sizes: house 1, house 2, house 3, and house 4. And our question says for each house determine the total number of pieces needed. Well, since we've got a picture, all we really need to do is count, and I'm just going to put the pieces up underneath each of the pictures and not put it on the line there. So for house 1, I have 2 squares and a triangle. That's a total of 3 pieces. For house 2, I have 4 squares, 2 triangles. That's a total of 6 pieces. For house 3, how many pieces do we have? Right, we have 9. 6 squares, 3 triangles, 9. And hopefully at this point you're starting to see a pattern. You always want to confirm, go out a little further and make a prediction and then see if you're right. So for house 4, make a prediction, then count it, make sure you're correct. If I think I have a pattern here, my prediction might be that the next number would be 12. And if I count, I have 8 squares, 4 triangles, that makes 12. Okay. So how many squares and triangles are needed for a given house? Organize your information in some way. So I'm going to slide this up just a little bit. And let's make a data table. And we want our table to reflect. Let's actually do a couple of things here. Let's do the size of the house. Let's do the number of rectangles and the number of triangles, just to see if we see some things going on, and then number of total pieces. Okay, so my house numbers are 1, 2, 3, and 4. In a 1, we had 2 rectangles, 1 triangle, total of 3. In a 2, we said we had 4 rectangles, 2 triangles, total of 6. In our house 3 size, we had 6 rectangles and we had 3 triangles for a total of 9. And in our house 4, we had 8 rectangles or squares and we had 4 triangles for a total of 12. So I see my pattern happening here in my total column. I also see a pattern happening with my triangles, and I see a pattern happening with my squares or rectangles. This is 2, 4, 6, 8. Every time my house size increases, the number of squares or rectangles increases by 2 as well. And every time my house size increases, my triangles go up by 1. And over here, that increase of 2 and that increase of 1 means that each time I'm increasing by 3. So like in the previous video, as I go up by 1 in my input, or I could call that my x or my domain, my output, my range, my y values go up by 3. Again 3, again 3, again 1, and again 1. So to me that looks like a linear relationship, and I'm asked to describe what house 5 would look like. You have a couple of options here. You could draw it. We can extend our data table, which is what I feel like doing, and come up with an answer that way. So if I have 5, following my patterns, I would expect to have 10 squares, 5 rectangles. I would expect, as I increase by 1, to increase by 3 here for a grand total of 15 pieces. So house 5 would look like 5 columns of squares, and that would be a 2 by 5 rectangle with 5 triangles on top. I'm asked to draw a sketch of that house, so I'm just going to do a pretty fast sketch here. Since I told myself it's a 2 by 5 rectangle, let's just do that. Let's build a rectangle. Doesn't have to be perfect. 1, 2, 3, 4, 5 columns. It's a 2 by 5, so there's my 10 squares I said I would have. And then on the top of each of those, I'm putting on a triangle. This is a size 5. Okay. Predict the total number of pieces you will need to build a house 15. Explain your reasoning. Well, if I've got this linear pattern up here where every time my house size increases by 3, and if you look back at our table, I could get my house size to this answer. How do I get a 1 to become a 3? How do I get a 2 to become a 6, a 3 to become a 9, a 4 to become a 12, and a 5 to become a 15? Well, it sounds like take your input, or your x value, times 3, and you'll get your output. So that sounds like I have a rule. So I'm going to actually jump to the very bottom with that idea, write a rule that gives the total number of pieces needed to build any house in the sequence, and I'm going to say total pieces equals 3 times house size, where h is equal to house size. Okay, so 3h, or I can just rewrite it as t equals 3h, where t equals total pieces. Okay, so if I know that, not only am I going to be predicting it, I'm going to actually have an answer to this. If I know a house 15, and I input a 15 into my formula for my input, what would my output be? It would be a 45. Okay? The house pieces increase by 3 pieces for each size you increase. So I could extend my table, keep going all the way down to 15 from up above, or I can just I could draw a picture, I could do a whole bunch of different things on this, but a rule really makes this easy. If I have an equation or a formula, I can solve this quickly.